Good afternoon, everyone. Welcome to the segment routing session at Cisco Live Melbourne. First of all, thanks for selecting my session. It is an honor to be back in Australia. I was here last year. I did not have a session, so I do have one this year. My name is Jose Liste. I am a technical marketing engineer. I work in San Jose, California. And I have been involved with segment routing for quite a few years. Not quite from the beginning. Segment routing is no longer new, but it's been 7, 8 years working on segment routing. So helping service providers, helping some of the web operators, helping large enterprises adopt SR. Okay? I hope this chit chat was enough for you to get my accent. So it will not be a problem from now onwards. But if it is, sorry. All right. We have a small clip for you. Maybe you have been seeing that in other sessions.
Hi, my name's Mandy Nicholson. I'm a Wurundjeri woman, a traditional custodian of Naarm. Wamanjika Kirapik. Welcome, my friends.
All right. Thank you, Nick. You have seen this slide. I will be moderating this space until, I think it's quite aggressive, almost until Christmas. But feel free to leave questions there, and hopefully we'll get back to you. What is the goal of today? The goal for today is to give you the latest and greatest on segment routing, what is happening in Cisco's implementation of segment routing for SR-MPLS and also SR-PCE. What are some of the key building blocks that you may not fully understand that we will be able to cover in the next 90 minutes? That's all fair game. We have quite a bit of an agenda. I selected these topics you see here. To me, they are very important, that it will be great for the people in the room to be at the same level. There are many other topics that we're not covering. But if you have any questions, based on the amount of material, if you think you can hold on to your question to the end, do so. If you want to ask right in the middle, go ahead. But otherwise, I will be here afterwards outside. I'm assuming some level of knowledge for segment routing, SR-MPLS, and maybe less knowledge, but equally so for SR-PCE. We're not going to cover one-on-one material content. There is plenty of Cisco Live presentations that you can find in Cisco Live 365. So my idea is just to go over the latest features and also some of these silver bullets that I feel people don't know enough. Okay. All the materials are about iOS XR implementation. However, it is very exciting for me, and I'm here with our PM, Yannick Semko, as well in the first row. We have SR-MPLS in iOS XE. We have SR-PCE in iOS XE. So there are catalyst switches that have SR-PCE implemented. So, but today we cover iOS XR. There are two siblings in the segment routing family. One where we run the MPLS data plane, so an instruction is an MPLS label. The MPLS label will tell the packet what to do through the network. So we do source routing with MPLS. That was easy. No changes to the data plane. It's pure MPLS operations, just a control plane upgrade. The other sibling, we don't call it a baby anymore. It's already standing on its own, is IPv6 data plane for SR, is called SR-PCE. Now here, we encode instructions inside of an IPv6 address, or what it looks to be an IPv6 address, or 128 bits of information. And we're not encoding one, we encode one or more into one IPv6 128-bit field. And that is SR-PCE. It came later, There was some standardization to happen, some data plane changes, but it has been out for 5 years. I'm going to do a few clicks. I like this visual where you can see the simplification that is happening at the protocol level with segment routing MPLS to start. Pure transport, we take the MPLS data plane, no changes, and we compare the protocols that I needed to use for advertising routes with prefixes and protocols for labels and then protocols for protection. And then you look at the right-hand side, I do everything with my IGP. So my IGP has the extensions to do everything that I'm doing on the left with 3 protocols. Intra-domain, if I now go inter-domain, I have typical seamless MPLS with BGP-LU giving me reachability end-to-end across domains. On the right-hand side, we have an augmentation of BGP-LU that we call BGP-SR. And then we bring an SR-PCE. So with BGP-SR, we deliver the end-to-end best step for paths in multi-domain. And with the PCE, we offer other type of intent. For example, minimization of delay across multi-domain. Now, the next click has nothing to do with us. This is now the services. In SR-MPLS, there are no changes to the service layer. So multi-protocol BGP or LDP were used to signal service constructs. But the evolution that was happening in parallel to SR is the evolution of EVPN, where now I can use the BGP control plane to signal services, L3 or L2. Most of our customers are doing both journeys together. They embark in the service journey and the transport journey. You don't have to do it both at the same time. They are unrelated, service and transport layer. Now we look at the same evolution for SRv6. We start now with the MPLS data plane. That's the classic. We look on the right-hand side, and we have the IPv6 data plane, because now we are trying to do source routing with the IPv6 encapsulation. If we look at the left, the protocols, they don't change from what I had earlier. Nick, the click is not too reliable. But okay. Same as before. If we look at the right-hand side, we are going to have, the click is not working well for me. Just one moment. Yeah. Okay, I'm going to keep trying. So now we have my IGP routing protocol for IPv6 with extensions. So I do my routing, my intra-domain path. We put LSP in quotes because it's not a labeled path anymore. Huh? And I do my fast reroute and my traffic engineering. Yeah. No. My multi-domain didn't change on the left, but now take a look at the right. We are simplifying the routing design, so now I don't need to have BGP-LU on the top. For the first time, for us in service provider, we can now remember something that we were never able to do, which is summarization. With MPLS, I need to do host routing, so these /32s will have a label that is understand. I can have an LSP. With SRv6, I can summarize these special prefixes that I'm going to use for transport semantics. So summarization will bring a big shift in the architecture. It's going to simplify what my routers will have to advertise, what my routers will have to program. And at the end of the day, I'm not doing host routing anymore. Okay? On the services, we do use eVPN or BGP for L2 and L3. But if you look at the big dotted line, it's very important. Both transport and services are being signaled as part of the SRv6 source routing paradigm. So now there is a connection between the transport and the service, and the routers will be advertising SRv6 functions for both transport and service. First time we get to collapse the signaling of the transport and the service. So when you start to design your segment routing network, especially for MPLS, one of the first things you have to do is design your global block, or SRGV. The global block is what we use to align and allocate the prefix seats. These are the labels that represent a router, a loopback on the router. And this segment routing global block needs to have a size. How big is it need to be? Is typically the number of routers that you have in the network. So designing your SRGV is the first task that you have to do. The key question for a service provider or otherwise operator is, when I configure my SRGV, do I need to reload the router or not? Can I save myself from a router reload? Because what we're doing is we are allocating a label block, and if the label block is utilized by other protocols, I cannot insert SR and ask for that block. So then I will need to reload the box. So here we'll give you two techniques where you may save yourself from having to do the reload. Most likely, we have been shipping SR for over 10 years. The software that you have running now already has SR support. So you may not need to do a software upgrade unless you're chasing for a new feature. So if you have a reasonable size network of 1,000 routers, you might not need to reload the router. The iOS XR label manager will preserve a block from 16,000 to 24,000 so that nobody will get there, even if you don't have segment routing enabled. So if you have a segment routing capable image and you have a network that has, when I tell you 1,000, I will tell you why I said 1,000. But it could be up to 8,000 routers. You don't have to reload. The block will be waiting for you. We call that the preservation of the SRGV. Okay? Oh, this click is going to be fun. Let me go back. Yeah. Let's give it a try. If not, I think we'll switch to my computer, because I think before it was working better.
We're just getting another thing that dropped off for you, sir.
Okay.
Should be a couple minutes.
All right. Thank you, Nick. Yeah. Yeah. I can go without slides, but then it will be a... Can you advance for me, Nick, there? Or? Yeah, let's do it. So then I'll use you until we get the new clicker. Forward, please. Forward. But if you decide to have an SRGV that could conflict with other devices, you may need to reload. Next slide. However, we have options. Imagine you have the label block as shown on the right, and here the ranges in green is the preserved range that we have available ready for you to go. It's up to you if you want to use it. The red lines are people grabbing labels from the label dynamic range. If you choose, next click, if you choose an SRGV that is free, high enough, here I'm showing hypothetically the 400,000 range, and I'm giving it 32,000 labels, nobody's there, you're going to be able to allocate the SRGV, you do not have to reload. Right? So many customers use this technique to prevent the reload. They look at their network and they see that the middle or the high-end numbers are not being utilized, so then you are able to squeeze in a new SRGV according to your size and not have to reload. The configuration of the SRGV is shown on the slide, on the top, on blue. The command on the bottom is a very important command. This is the #1 command I will put in my MOP to validate if the SR-GV was successfully allocated. If it's successfully allocated, it will show like on the slide. If it failed to allocate, you will not see this output. We must have the SR-GV allocated properly. You will also be getting alarms and syslogs in your router console. Okay? But this is a very important comment in the bottom. Next slide. Yeah, we have a few clicks, so go ahead and do 2 clicks. In here, we have configured a non-default SR-GV. I said I want to go from 18,000 to 20,000, and then I can verify that it is allocated. So you choose the beginning of the SR-GV and how big it is. So the configuration will allow you to put those 2 values. Okay? Next. One more time. One more time. One more time. One more time. What are the recommendations for the design of your SR-GV? Next. There are 2 ways to configure the SR-GV in iOS XR. The bottom one we don't recommend. We had this back at the very early days where you configure the SR-GV under the routing protocol. What we want you to do is configure the SR-GV globally. Segment routing global block. That way, multiple IGPs that have SR enabled, or even BGP that has SR enabled, will be able to grab the SR-GV that you have globally configured. So, number 1, configure the SR-GV globally. And we have a new clicker. Let's see if it works better. All right, it seems like it. Okay. Whew. Okay. There are 2 main goals that we want you to follow. One, try to have a homogeneous SR-GV across the network, meaning all the segment routing devices in the network will have the same range configured, starting point and size. That's homogeneous. Therefore, when you have a segment routing LSP, the label will be globally unique. When you troubleshoot, one label will be the same local label across all the devices. If you cannot afford, because maybe you have another implementation that will not give you the same space, you will have what is called a heterogeneous SR-GV. Different label ranges, but they're all the same size, but they're in a different location in the label range. It doesn't break SR, it breaks the global unique segment routing label end-to-end. That's a bummer. The second rule is for everybody to understand. A prefix is owner of one label in that block. There is a one-to-one mapping. You cannot have another prefix that claims to have the same label from the global block. You are responsible for making sure that the collision does not happen. If the collision happens because you make a mistake, you will get alarms from the devices. But otherwise, one-to-one mapping between loopback IP and the label from the SR-GV. However, there is a very important case called anycasting, where you could have 2 routers advertising the same prefix with the same label. I'm not breaking the rule. It's 2 routers saying prefix X has label X. That's IP anycasting. That's allowed. The way how we tell people to manage their SR-GV, you have flexibility. In one approach, we say, go ahead and configure in gray a common SR-GV across the network, like so, 16K to 24K, and then you micromanage pools for different regions in the network. So the ranges in orange, in green, and violet is you doing the management. So if you have a router in the core, you're going to give them a label from 16K to 18K. If you have a router in the access domain on the left, he will get a label on 22K to 23K. So you have these micro ranges that are purely a task on your end. The routers have configured the SR-GV in the bottom. This is one approach. The other approach, first come, first serve. A router comes in, I don't care what it is, what is my next label available? You give them that label value. First come, first serve. You are more efficient that way. You are not wasting labels in case these micro ranges are too big and then you don't have enough population. So either one will work. Okay? So you have these two choices. Yeah, okay. How many labels do I need to count or expect to have in my sRGV? And you have to think like this. A router has a loopback. That loopback is my BGP next hop, is the anchor of the LSPs on that router. So I will have one label that represents that IP address of the loopback. It's called the prefix SID. So at least one label. So if I'm doing an sRGV of 8,000 labels, I have 8,000 routers. That's a lot of routers for many companies. The number can go lower later when we start doing what we call flex algo, where a prefix could have multiple labels. So let's say I'm a router, I'm Jose. I could have a label to tell people, come to me through the shortest path based on IGP. Or come to me based on the shortest path based on delay. That's a second label in my loopback. So we have what we call flex algo labels. And typically, what we see people doing with flex algo is in the single-digit area, one flex algo to implement delay-based routing, one flex algo for a premium service where I have a T metric assigned, maybe a flex algo for dual planes for resiliency. So we're looking at 3 to 4 flex algos in the network. We take it forward and say multiply by 2, so you have 8 flex algos. So you have 8 labels per router. That's why I said earlier, with 8,000 labels, you could handle very well 1,000 devices, assuming a very, very aggressive deployment of flex algo with 8 flex algos. So that's the recommendation we give people. Think single-digit ballpark for flex algo. Okay? TI-LFA. To this day, TI-LFA is the #1 reason why people deploy SR. People want to have an automated, optimum backup path computed by the IGP. So I don't have to do MPLS TE for FRR. It's all done by the IGP. I run an SPF for the primary path, and then I'm a router, I have an interface. I remove that interface from my database, and I run another SPF. So any prefix that went on that interface is now being protected by a backup path. I pre-compute those backups. It all happens automatically. You don't have to worry about it. You just configure one line, and you're done. So TI-LFA, topology-independent, loop-free alternate, uses source routing to guarantee that the IGP will find the backup. Of course, you need to have enough interfaces. I cannot make magic. But if I have interfaces, I will be able to find a loop-free path. There are many flavors of TI-LFA that you can configure on the router, and that's going to be shown in the next slide. If the clicker cooperates. There we go. Oh, I have yeah. It's still very slow, Nick. I don't know. All right. So there are many types of protection that you can turn on the network. You can ask the IGP to pre-compute a backup path that protects, assuming that a link has failed, link protection. Assuming that a node has failed, that's node protection. Assuming that a link in an SRLG has failed, that's local SRLG protection. Combination of the two, that a link in a local SRLG that has common SRLGs remotely on other parts of the network has failed. These are all done by the IGP. So that's the TI-LFA, very popular. That's why people do SR as the first trigger for going down the segment routing deployment. Now, a couple of less known things. Over time, we have implemented different knobs to provide a selective guidance to the router or who to compute backup for. So the first thing we did is we want to control how many ASIC resources do I use for programming backups. If I have a platform that has restricted limit of resources, let's say they're not ASR9Ks from back in the day, I need to watch my resources consumption. So we're giving you knobs to be very selective on what you want to get program backups. It's not that you don't care to program everything, but if you program everything, maybe you run out of resources in the ASIC. And that's the mentality of these knobs, okay? So in one case, we use the prefix priority in ISIS, for example. So you have prefixes of different priority. I'm going to use my laptop, Nick. It's too painful. So we can tell the IGP, based on the priority of a prefix, I want you to compute backups only for the higher priority prefixes. And who are the higher priority prefixes? You decide, or you can take the router defaults. But typically, your loopbacks will have higher priority SPF prioritization in the IGP. Okay. So if you can switch me to here, will come from this. And then I need the receptor for the clicker here, so I can drive the clicker locally. Thank you. We are right here. Thank you. This is going to be much better. Let's see. Okay, very good. One feedback I received recently in Cisco Live is people really want to see configs, so they get an extra handle of what I'm saying. So you will see a lot of slides that have configs. I'm not going to explain every line, but I will say something that say, okay, here it is. Jose told me that. I will look for that slide later. You guys will get all these slides anyways. So here you have different type of priority thresholds where you can tell ISIS, I want you to pre-compute backups only for prefixes with that priority. There's another feature which is called segment routing micro-loop avoidance that is going to fix the 20, 25-year-old problem in IP. When interfaces go down or interfaces go up and routers converge at different time, I may have micro-loops. And I don't have a way to deal with micro-loops other than waiting for the micro-loop to go away. With SR, you can have a solution for micro-loop avoidance. In this knob that we are shipping in a couple of weeks from now, you will see the target release on the top. If I show you a feature that has no green box, it means it's an old feature, quite an old time. But if it has one XR mention, it's because it's actually in the last year or so. So we have new knobs as well in micro-loop avoidance where you can now specify for what prefixes you want to do micro-loop avoidance. Again, the mentality here is if I do micro-loop avoidance for everything, I may not have resources. So again, I want to be very specific and I want to do avoidance only for some. And that's your knob. So those were the two key new things that we were doing on TILFA prioritization are selective backups. The third topic here is BGP segment routing. This is where we use BGP-LU to signal end-to-end LSPs, but now the LU local label is global. Imagine you have your LU speakers and the LU inline route reflectors and the egress PE all agreeing that the IP of the remote router in the other domain has the same LU local label across. And that is what we do with BGP-SR. BGP-SR effectively represents the BGP best path to the prefix. BGP-SR completely uses BGP-LU NLRI. So BGP-SR is BGP-LU with an augmentation in green of the so-called BGP prefix seed attribute. And in that attribute, we store the index of the prefix. And with that index, when I receive the LU route, I look at my sRGV and I pin down the label for that prefix. So that extra hint is the BGP prefix seed attribute. Otherwise, this is BGP-LU, is completely interoperable with other LU devices in the network that may not understand that attribute. The attribute is opaque, transitive. Okay? When you use BGP-SR, like I mentioned before, we want you to have configured the sRGV globally. Okay? Same recommendation as before. When you want to apply the index in the control plane, the slide shows you two ways on how to configure BGP-SR so that when I advertise my loopback, I will also set an index. So in this case, I have index 1 for my loopback of 1.1.1.1. So you are responsible in the IGP or in BGP to tell me what is my index in the sRGV. That's how you do it for BGP-SR. Okay? Now, people have asked me, okay, what is the value of extending BGP-LU to advertise the index? And one value is, oh, when we troubleshoot, we all look at the BGP-LU LSP, it's the same label all across. It's easier to take a look and inspect the label cross-connects based on that label value. I don't have to be checking a different local label across the point. I think I say, good, good. But that may not be good enough for me to make the jump. With BGP-SR, we can now increase the resiliency in the network, and that is a big deal. Imagine you have two ASBRs that are learning a remote BGP-LU route. These two ASBRs will have the same LU local label for that prefix. And they signal the label, the LU path, to the ingress PE. So now this is a big difference. In the normal LU, my ASBRs will each signal me a different label. Well, now they are synchronized because of the index. So now I'm going to be able to do something that was not possible before. I'm going to be able to use Anycast as a BGP next hop for LU. So the two ASBRs, when they advertise these LU routes, they will advertise from the same next hop. It's an Anycast next hop. So now you can get 50 millisecond protection for node failures. Pictorially, look at this. I have my ASBRs 1 and 2, and then I go across. If I have a failure number 4, this is the ASBR 2 fails. I'm now depending on my IGP plus BGP peak convergence. That's normal. But when you do BGP-SR and the labels of the ASBRs are synchronized, and you enable the Anycast address on the ASBRs, and you make the Anycast be the LU next hop, now you get 50 millisecond protection based on ISIS or the IGP fast reroute. Because what's going to happen is the IGP will just take me to the next surviving node that is advertising the Anycast. And that's how you get 50 millisecond for node failures. What are some of the operational considerations for using Anycast? Because when you advertise the Anycast address as an LU next hop, you will be attracting traffic. But are you ready to switch traffic to the other domain? And that is the key question. How do I make sure that me telling the world that I am the owner of an Anycast, and people are coming to me, and that I'm ready to switch traffic. So we implemented features that we called conditional prefix advertisement in the IGP. So imagine you have a router number 1 that has an Anycast that he will advertise in domain 1. But for him to make a decision to advertise the Anycast in domain 1, he checks if I have reachability to 2 IPs in domain 2. And if I have reachability to those 2 IPs, then I advertise the Anycast. And if I don't have reachability, I don't advertise the Anycast. This is called conditional prefix advertisement. Here's the config of how you do that. You see on the top, you have a prefix set. You put the list of prefixes that you want to check reachability. And when none of them are reachable, then we stop advertising the Anycast. That was our first phase. Later on in iOS XR object tracking, we implemented BGP neighbor tracking. So now I have an object in XR that will check, do I have a BGP session with Yannick in this address family LU? Have I received EOR from Yannick? Do I have all the routes from Yannick? Did I give myself time to program the routes in my forwarding? And if the answer to all of that is yes, a object will be up. So we call that neighbor tracking via objects. And that feature is also quite old. It's from 7.7.1, I think, a long time ago. But now we have connected the two together. Now I have the next generation of ISIS conditional advertisement that is tied to objects. So now I have router number 1. He has a loopback, Anycast loopback that he can advertise to domain 1, but he's now checking if his BGP neighbor to router 2 is up in the address family. Have I received EOR? Have I given myself time to download? And if the answer is yes, I advertise the Anycast. This feature is going to come up in Feb of next year, 24.1.1. But here you have the config. So here you have your object on the top. I'm going to call it, how do I call it? Yeah, it's called nay_obj, and then that object has an RPL, and then I attach that RPL to the IGP configuration. So in my LU example earlier, the ASBRs can track their neighbors to the other domains in the LU address family. And if my LU neighbors are up, then it's safe enough for me to advertise the Anycast. Okay. That's our BGPSR section. Switch topics to what we call color-aware routing principles. This is the principle of operation for SR traffic engineering, and that's what we'll explain. Marketing-wise, we talk about intents. They are real, they're not fluffy. An intent will be a transport intent, as an example in this bullet list. Give me a path that minimizes the expected delay based on the expected delay on the links across the network. Give me one that minimizes the delay based on the measured delays on the link. Give me a path that maybe will give me disjointness from another path. Give me a path that will stay in different planes. Give me a path that will avoid certain pockets in my country or pockets across the world. I don't want to traverse some countries, so data sovereignty. These are all intents. And what we're trying to do is realize how easy can I make a BGP service route follow a path that will give me that intent? And this is what we call color-aware routing, because the intent is expressed in what we call a color object that is nothing but a color BGP extended community. And that's the concept. So intent. Intent is placed onto the BGP overlay route as a BGP community. So a color blue in English means low latency. Orange means low cost, low IGP. In real life, these not English words. These are actually BGP encoding of extended community is a number. Right? So you have your color routes that carry the intent, and then you have the color-aware transport routes that satisfy that intent. Okay? And the last bullet is the key. A color service route is steered over a color-aware route of the same intent. That's the big concept. And this should leave you wondering, oh, wait a moment, so if really the BGP route carries the intent, if I change the intent on my overlay route, will the network just automatically follow? And the answer is yes. So here's an example. A egress router E is advertising prefixes from a VPN. It's an L3 VPN, so I have two prefixes in letters, V and W, and these prefixes are coming with a BGP next hop, with a label, everything, but they come with a BGP color extended community. Here, I use English. I don't put the number, but I'm going to use color orange, color blue. These are my color routes. And these colors, and these routes are coming in color from the egress PE. Here's the BGP color extended community. It's completely standardized. You have the RFC numbers. What can I apply color to? BGP service routes. Who are BGP service routes? L3 VPNs, EVPN, Internet Global Routes. So now we switch to the color-aware transport route. A color-aware transport route is a transport object that satisfies an intent, and it is identified by a color and the egress or endpoint that he's trying to go to. So you see, we call them E, orange, E, blue. And I do have two paths in the network that will represent the intent of those color-aware transport routes. There are many ways how we can realize a color-aware transport route in a router. And we will see that in the next two clicks. But before we do that, this is a very important slide because it shows the magic moment, the coupling of the service route with the transport route. I have a service route that has a next hop, BGP, and it has a color. Next hop E, color C, because the route came from E, and I put color C in it. Then now I have, on the ingress router, I have a color-aware transport route, E, C. And that color-aware transport route has inherently a path through the network. And now you see the connection between the two yellows and the two greens. The color of the service route matches the color of the transport route. The BGP next hop of the service route matches the endpoint of the transport route. And if the two match, any incoming traffic on A that is trying to hit the forwarding entry of the prefix V will follow automatically that transport route. And that is what we called automated steering. I do not have to go, if I want to change the intent of the transport route for the VPN prefix V, I just change the color. And then A will try to find another transport route to carry the prefix. It's completely automated. I don't have to go to A for anything. Okay? That is the big concept, automated steering. So how do I realize transport routes? One way is with FlexAlgo. Many of you may have heard FlexAlgo. I cover FlexAlgo at length coming up, but FlexAlgo is one way where I can realize a path that takes me from E1 to E2 in different directions. I have here two arrows. And the beautiful thing about FlexAlgo when you use it in MPLS is a very fancy path with only one label. So I don't have this physics things going on, label stacks. No, one label. So maybe the orange is mean delay and the other one is mean IGP. So very efficient encapsulation. So FlexAlgo provides color-aware transport routes because on E1, he will associate color orange with a particular FlexAlgo. So. The second one, a segment routing traffic engineering policy, SRTE policy, AKA SR policy. An SR policy is and was born from this color-aware routing paradigm where I have a policy that has an endpoint and a color, and it has a path. And that path has a stack of labels. It is an SR policy, so we're not using signaling of the SR policy. It is not an MPLS tunnel. It is not an SR tunnel. It is an SR policy, completely source routing. So an SR policy is also a color-aware transport route. And here it is, the SR policy. SR policy has been standardized, RFC 9256. If you want to have a read, it's actually a very good read of the SR policy architecture. It explains all the elements of a policy. But for you to know, it is a forwarding object that is completely stateless, that it has a path, but it is identified by a color and an endpoint. And these are what I need to do automated steering, color and endpoint. In addition to ODN, automated steering, there is a concept called ODN, on-demand next hop. And I'm going to explain to you how ODN workflow looks like. Here, in step 0, E2 advertises the BGP service route with the color. In step 1, E1 recognizes that it has received a route with color blue, and he knows what color blue means. It means low delay, but it is a recipe, it's a template. E1 does not have a policy for that intent going to E2. So what ODN will do is once I receive a route with an intent, the template will make E1 to create a policy on demand, and hence the name ODN. We will automatically create the policy with a blue arrow, which has a path, that will then take traffic over it. So ODN means the on-demand instantiation of the SR policy on E1. And what triggered the instantiation? The BGP service route. So if I receive the first route for the intent, and I do ODN, I create my SR policy to him. More routes come in, service routes with the same color, they all share the intent. When the last route is withdraw, the policy goes away. That's ODN. On-demand next hop. So with automated steering that I explained earlier, I put a color to a service route, and then all the traffic to that color route will follow the path of one policy. So we call that per destination automated steering. But what happens if you want to do more and you want to do per flow? Some traffic to a prefix, I want to go one way, but some other traffic to the same prefix goes another way. And when I say some, it could be a DSCP marking on the traffic, or maybe the source IP address of the traffic. This is what we call now per flow automated steering. So the network can give me two paths, a black path, which is the black arrow, or the green arrow. And my goal is to say, if I need to send traffic to the BGP prefix 3/8, I want to follow the green arrow or the black arrow, maybe based on the DSCP value of the incoming traffic. And that is the motivation for per flow automated steering. So with per flow automated steering, what you are going to do is we're going to create on the router number 1 is these blue tentacles. We call that a PFP, per flow policy. A per flow policy is also color and endpoint identified, but instead of having one path, it has an array of paths. So my array in this drawing is path number 1 is the black, and path number 2 is the green. The traffic coming in will be classified at the ingress PE, and then according to your classification requirements, it will be put on the green or the black. And this is what we call the per flow policy, which will give me per flow automated steering. I'm going to say something quick but important. The blue PFP, as you can see, it doesn't leave the router. It doesn't have a path. It has an array of paths. And that is what the blue reach is inside. But this blue PFP will have a color. So if you put that color onto your BGP routes, only those routes will receive the benefits of the per flow behavior. Other routes that don't have the color of the PFP, they just go business as usual. So you can be very selective who gets the treatment and who doesn't. So those are the principles of color-aware routing, automated steering, ODN, SRTE policies. Now we'll come back here to a function called the PCE. And I mentioned the PCE briefly at the very beginning. It's a path computation element. It's just a function in the network that its job is to compute paths. Like a router reflector, its work is to reflect routes. The PCE computes. The PCE is basically a node that is capable to collect topology from the network, that has algorithms to compute paths, and it has protocols or otherwise APIs to deploy and instruct a router about a path that he computed. That's a PCE. The PCE also has northbound APIs to talk to applications. In Cisco, the SR-PCE that you see in that circle inside in the middle is basically an iOS XR router that you enable the PCE function. And on the top, you have the automation Cisco Crosswork application suite of CNC or COE, Cisco Network Controller or Cisco Optimization Engine. Okay? So the idea here is that, and you can see on the arrows, the PCE can receive topology information coming from BGP link state, BGPLS, or IGP, and then it can use, for example, PCEP as a protocol to talk to the network. But the question now here is, why did you brought the PCE to the conversation? Does SR always needs a function like this to compute? Or what is the context here? The context is as follows. If you want to compute multi-domain paths across multiple AESs, multiple IGP domains, multiple levels, you need somebody who knows the entire topology to compute. And the PCE is the guy that has the multi-domain topology, so therefore, with his algorithms and the multi-domain topology, he computes. A router sitting in one IGP, one level, one area, doesn't know the entire network, doesn't know the entire topology, so I cannot ask that router to do it. So this router, if he needs to compute a path to the other side, he will ask for help. So he will ask the PCE, hey, can you give me a path? But here I will make a very important comment, because I started talking about BGP-LU and BGP-SR. In multi-domain networks that already exist today, you are using BGP-LU for your best effort. I'm not advocating here that you have to put a PCE in order for you to kill LU. No, don't do it. LU is the best effort. You bring the PCE for the other SLAs that you might have, like delay multi-domain path. Okay? So that is the context for bringing the PCE to the drawing. Otherwise, if you have this humble router that is sitting in an area, he has a topology, he could compute for his local, for anything that is within the local topology. So again, SR is not depending on a PCE. The computation can reside on a router. It can reside on a function like the PCE. The difference between the router and the PCE is how much topology do they know. And that's the SR-PCE. So as you can see here, I use the terminology distributed or centralized. That's referring to the head-end computing or the PCE computing. And typically, the column on the right, which is the multi-domain, is where things become centralized because it's multi-domain. I don't have topology. There is one problem, though, where one of the rows that I am single domain and I still need to have centralized, and this is the problem of path disjointness. If I need to compute two LSPs from two head ends to two tails, a router doesn't know anything about other LSPs, so I go to the PCE. So when do I need the PCE? It depends. How far are you trying to go, and what type of problem are you trying to compute? Okay. And this is what this table is trying to give you an idea. The PCE is a layer, it's a function sitting on a layer. The PCE is not a God box. Nobody's going to deploy, because Cisco said so, to put a router in the network that's going to take care of all the computation, and that's it. The PCE is even though I use the word centralized, it's a scale-out layer where you have layers of PCEs that are taking care of its population of local routers. Okay? So I'm a PCE sitting in a region. I take care of computing for my people. I know the entire topology, but if they need help, I help them. And people in the other region will have another PCE that will compute for them when they need to come back the other direction. Remember, an MPLS LSP, an SR policy is a unidirectional path. I'm going in one direction. Yeah? So the PCEs are not a God box. It's a scale-out layer where you deploy them in regions, most likely. And the picture here will show. So I have 3 domains, and the domains will have PCEs assigned to take care of a particular domain. The PCEs in a domain will receive the multi-domain topology through BGPLS. So the dotted lines is really the BGPLS information traveling through the network. As you can see, we can see the topology flowing from domain 3 to domain 2 to domain 1. With the multi-domain topology in LS, then they can build and stitch a multi-domain topology. Then they are ready to receive requests for computation. Yeah. In some cases, the domains are connected by common routers, like BR1, BR2 is one router connecting to left and right, 2 IGP process. In other cases, I have a BGP handoff. So I have an inter-AS scenario. In that case, even though I'm not going into the details, there is a segment routing instruction called EPE, egress peering engineering, where you will enable EPE on those eBGP neighbors in order to allow the PCE to stitch the 2 ASs. These PCEs in the region can be deployed in pairs. And then what we use is we use well-known HA model from the router, where the router is connecting to both of them via PCEP. And at any given time, he has one PCE that he will delegate to, say PCE A, and I have A prime. So I will keep asking A. And if I see that A went away, I will ask A prime. So it's all what we call PCC-centric high availability. So the PCC will take care of going to the other PCE to delegate computation. And that's really what this is saying. This feature, I'm very excited and bullish because we see it being used a lot. Sometimes in PCEP, my PCE is powerful. Maybe PCE can compute based on delay, but my routers don't know or they don't support the PCEP object to ask for delay. So the routers are behind in their capabilities. They just don't support a delay PCEP object. So they cannot ask me for delay, or they cannot ask me in a way that the PCE will understand. In other cases, with FlexAlgo, I could have a multi-domain topology with FlexAlgo, but the PCCs cannot talk FlexAlgo objects, so then I'm stuck. I need to go ahead and do a massive upgrade of my PCCs eventually when the PCC is supported. But can I do otherwise? And yes, you can do otherwise, and the feature is called override. And what we do is we let the PCCs do their thing and say, hey, I'm Jose, and I need to have a delay LSP. And I put that keyword delay in the name of the LSP. Then what I do with this feature, I will be paying attention to the name of the LSP. And if it reads delay, I know that you really wanted to have a delay path. So we match on properties that are supported by the PCC to do something else. So I put the example here of a PCC that does not support the latency metric, but the PCE does. So I just put a clue in the LSP name, and then now the PC will say, okay, I know what you really want. You don't want IGP, you want delay. And this will prevent me from having to do a network-wide rollout of PCC upgrades. So here you have the CLI for the config. You have a so-called matching criteria. What am I going to be matching on? And what am I going to be overriding to? Okay. So that's the sample syntax, and here you have a configuration. So in the top, if I have any LSP name that has the word delay, the PCE will say, okay, you want delay optimization, even though the PCC did not ask for it. Or if I have an LSP name called Flex 128, I'm going to say, oh, you want Flex Algo 128 path computation. And that's what the PC override will do. And since we talked about Flex Algo earlier, here's Flex Algo. Flex Algo is the most effective way to do SRTE because of its power and its simplification. With SRTE, with Flex Algo, a tool in the SRTE toolkit, you are going to be telling the IGP, OSPF, and ISIS to do SPF's, shortest path first computation, based on your needs. Not only the IGP metric SPF. I can now do an IGP, an SPF based on the TE metric. I can do an SPF based on the delay on the links. I can run constraints and say, I'm going to use affinities, link affinities on my links to run SPF based on those constraints. I can do an SPF based on the interface speed of a particular link. So the IGP is getting more job, but it's a job that he can handle very well beyond just an SPF for the IGP metric. And we call it flexible because you decide what metric and what constraint you want to do in a particular instance. So you decide what that Flex Algo will do. So here you have the same topology, and you have two different ways to go from 6 to 4. And those are an example of two different Flex Algos. And in English, on the left, I'm going from 6 to 4. Now, hear me out. Never going via 5, 1, or rather 8, which you cannot read, but trust me, that's 8. I'm sorry, no, it's not 8, it's 6. Or no, 6 is here. 2, thank you. Never going over 5, 1, and 2. Never, never, ever. I can only go via routers in the red shadow area. And I'm going to avoid links with the brown affinity. And that's my path, the red arrow. Same topology, and I say, okay, well, the same shadow area, I'm going to shadow area green. I want to go from 6 to 4, minimizing the delay across the network. So based on the delay on the links, I have a different path. This is one IGP, one loopback that will give me this power. And these paths, when I do them with SR-MPLS, it's only one label. Flex Algo is applicable either one to SR-MPLS or SR-V6. When you do it with SR-MPLS, you have an extra label for the loopback. Remember I told you 8, 5, extra? So that's your extra prefixed label for the Flex Algo. When you do it with SR-V6, you will have a different SR-V6 locator We'll talk about the locators at the end. Here's how you configure FlexAlgo. It's all under ISIS or OSPF. I have the ISIS here. Highlighted in red, you have the prefix seed algo. Basically, each FlexAlgo has an algo number, beginning on 128 to 255. So we call them algo 128, algo 129. And here you have the label for the loopback on algo 128, that's 18,001 or 16,001. That's how you do FlexAlgo in SR-MPLS. One line of config, and then on the top, if you look at the top, you have the definition of the FlexAlgo. We say FlexAlgo 128, metric type delay. That's it. That's all you need to do. Well, you have to do one thing. All the routers that you want to be in the red shadow area or the green, you tell them you are in FlexAlgo 128. So you determine the membership, which routers are in, which routers are out, and once they're in, what do they need to do? That's FlexAlgo. It's really a very important tool. Yes? Question?
So that prefix ID, is it allocated to a specific router?
Yes, so this prefix seed index of 18,001 label value is assigned to the loopback 1.1.1 of router 1. Yes. And if I do SR-V6 with FlexAlgo, on the top, on the definition of the FlexAlgo, I do the same thing. What I need to do now is define a locator, SR-V6 locator for the algo. If you're not familiar with SR-V6 config, we will have a quick reminder at the end. But you also do FlexAlgo with SR-V6. It's the same concept. What can I do with FlexAlgo? Well, I can now do things that are very powerful, very trivially, and one of them is multi-plane designs. I can have these routers on the top that you can see in the drawing, and the color around the edges indicates on what algo they belong. So I have routers that are in the green algo, routers that are in the red algo, and routers that are in both algos. So the PEs are in both algos. And now the loopback, back to your question, the loopback of router 9 will have 3 labels. A label gray, label green, label red. Now watch. First click. If I want to go to 9 across any plane, an ECMP between planes, ECMP inside the plane, I go and push the gray label of router 9. If I want to go over the green plane, I push the green label. If I want to go over the red plane, I push the red label. That's your multi-plane use case. You can now also do a delay-aware routing use case where the numbers in the topology there are the delay measured or the delay manually configured for the links. These are the minimum unidirectional link delay between 5 and 6 and 6 and 5 and so forth. If I tell ISIS to compute the shortest path based on IGP, I can go via the blue arrows, ECMP. But if I tell it to compute based on delay, this is my path. So I go 0569 with the green label. That's my mean delay path. How does the IGP, very good, very important point, how does the IGP know the link delays? They are flooded. So the link delays are link properties. There are IGP TE extensions. So we allow OSPF and ISIS to learn those delays. So the delays are measured. So I measure with my partner, and then I flood. And then everybody else in the IGP domain know the values. What happens if I want to realize a path that only traverses interfaces that have MACsec encryption, L2 encryption? Maybe I have a router that doesn't have MACsec on all the ports. So I have the green ports are MACsec capable, the brown ones are not. I could apply an affinity to those links, and they say, if you have the brown affinity, it means that you are in the clear, so therefore excluded from the FlexAlgo. If I do the best effort path, I traverse encrypted links and non-encrypted, but if I do the green label, I only traverse encrypted links. Only ever during primary or even backups. I can do TI-LFA for FlexAlgo, and TI-LFA in FlexAlgo will never take me on a brown link. So it's a very powerful, very strong concept. We have 2 new constraints in 7.11.1, which is shipping in a couple of weeks, where you can now use the interface speed as a constraint for the FlexAlgo. So now this FlexAlgo will say, I want to have a FlexAlgo that only uses interfaces of 100 gig and above. So I have a path that goes from 1 to 6 over 100 gig or 400 gig links. I skip the 10 gig links automatically. How do I configure? By the way, this is standardized. And here you have the configuration. So you have a minimum bandwidth config onto your FlexAlgo, and we follow what I explained. We have another constraint called maximum delay, where you can now say, if a link has more than X microseconds of delay, please prune it. I don't want to go over that link. It's not good. So the numbers you see in the topology with the D are the delay on the links. So now you could define a FlexAlgo that says, I want to use interfaces that don't have more than 12 microseconds of delay each. I'm not minimizing the delay. I'm, say, minimizing the IGP, but going over the remaining topology that excludes the links that have too much delay. And this is how you configure it. You have the maximum delay keyword, 12 microseconds, and that's it, they're out. Here there are some technical details of FlexAlgo. I'll try to go fast. But FlexAlgo introduces something that is going to be very powerful for you. We call ASLAs, application-specific link attributes. With the ASLA, we're now giving clients like FlexAlgo to have its own world. And what I mean, they have their own metrics. They have their own affinities. So if you're running MPLS TE, RSVP TE, or even SR TE from before FlexAlgo, and you have TE metrics legacy or affinities, FlexAlgo will use separate set. We call the ASLA values for FlexAlgo. So now you're open up to a TE metric that is used by FlexAlgo, which is unrelated from the TE metric that you use for MPLS TE. And the same with the affinities. You could have a different set of affinities for it. So here I'm giving you slides on how do you configure under the IGP, ISIS, you configure your metric type for the algo that we want to use. So FlexAlgo metric type, delay or TE. By default, we do IGP metric. Here's how you configure the TE metric for FlexAlgo in a given link. So the TE metric configuration is under the IGP, under the interface. And here's an example. You have FlexAlgo 140 is going to minimize the TE metric, and then you have 2 interfaces with a FlexAlgo TE metric of 100 or TE metric of 50. These are the FlexAlgo specific TE metrics. Here I have a FlexAlgo based in delay on the left, metric type delay, and then on the right, in iOS XR, you have the performance measurement configuration where you can have a manual delay, advertised delay 12 microseconds, or in the second interface, I have an active probe where I'm measuring the delay. Then, like I said, those delays will be flooded for everybody else's benefit. Oh, I have a FlexAlgo based in delay. I want to stop using that router for the delay because I'm doing a maintenance. You have your max metric delay or max metric TE, and therefore the routers will be last resource for a particular FlexAlgo based on TE or delay. Max metric. Here's an example of how you have a FlexAlgo that excludes or includes affinities. On the top, ISIS will now have the definition of the affinities, the bitmaps. Affinity foo, affinity va. Then I have a FlexAlgo 140 that says affinity include any foo or ba. And then in the next slide, in the next point, you configure the affinity foo or ba to the interfaces. All is done in the IGP. It's all IGP configuration. So here's how you do affinity constraints with FlexAlgo. TILFA. Remember, the reason why people wanted to do SR is TILFA. You have FlexAlgo TILFA support automatically. When you enable FlexAlgo and you have TILFA enabled globally, you get TILFA for the FlexAlgo paths. And here, I have an example of how the TILFA will realize a loop-free backup path for SR-MPLS on the FlexAlgo. Imagine that my FlexAlgo is asking me to avoid the red link. So I should never traverse the red link. And what I'm showing you now is after a failure of a link, the backup path in violet is not traversing the red link. So the primary path and the backup path for a FlexAlgo definition follow the same rules. This is with SR-MPLS, and for your information, I have one for SR-V6. So if you have the example of the encryption is the best case that you want to see that congruency of primary and backup always going over encrypted links. It's a very strong use case. However, many SPs are trying to provide low-tier services. People that don't pay enough to justify me for having resources used for backups. And they're not paying me enough for that. So, or marketing is saying, we have to compete, we have to sell cheaper services. So here you have a use case where you are asked to, can you give me a FlexAlgo path, but without FRR? And yes, in red, you can disable FRR for the algo. You can see that in the red box. Fast read route disable. Then that FlexAlgo does not have FRR. There's another area that we did work recently in iOS XR 7.8 and 7.11, where, again, going back to a world where we have devices who have limited resources, if I need to program a lot of ECMP paths for a labeled destination, maybe my device may run out of resources to program the ECMP. So I am forced, in some cases, to disable the ECMP. So again, pragmatic view. In theory, I want ECMP for everybody, but I cannot program it. So pragmatic view, I need to limit my ECMP programming. So here you have knobs to disable ECMP with very fine granularity. One granularity is that we do it at the algo level, so algo 0, max path. And what you do is you do max path 1. So when you say max path 1, if you had ECMP, you only program one path. So I can do max path at the algo level, FlexAlgo or algo 0, or I can attach a route policy, and the route policy can match on prefixes. So then you can kill the ECMP for some routes, but not for others. So this is the max path enhancement for granularity. And here you have example, okay? A max path 1 for the loopback of .100. So I'm disabling ECMP only for that route. Huh? And this has come up. Remember my question about offering cheaper services. I'm going to have one that does not have FRR, and now I'm going to say does not enjoy ECMP either. I'm going to give this customer only one path without protection. So here you have a FlexAlgo that has fast read route disabled and max path 1. So bare bone transport. No ECMP, no LFA, TILFA. How, and you know the answer because I said automated steering. How do I put traffic on an algo? When I do SR-MPLS, I leverage the SRTE policy. So the SRTE policy will have a path that has the FlexAlgo label of the destination. So it's a policy of a path of one label. Very powerful, but very simple also. And then I do automated steering. If I have traffic with a color, they follow the policy that has the color, which happens to ride on the FlexAlgo label path. With SR-PCE, I do not use the policy. Remember what I said at the very beginning, that the transport and the service are blended? In BGP, it's telling me the transport intent and the service intent in one block of information, semantically. So what the ingress P has to do is encapsulate into an outer IPv6. I don't need to do anything else. I put the traffic onto the algo directly with no policy. I don't have to even apply color to those routes. So in SR-PCE, we have a much simpler approach to realize the flex algo steering that is, when I say simpler, I'm not coloring, I'm not creating SR policies, I'm not using resources for those SR policies in the ASIC. So big difference on how we do flex algo steering. Here's a policy in SR-MPLS where the constraint is a flex algo label. Sorry, a flex algorithm, flex algo 128. So we say constraint segment seed algorithm 128. Yeah? And here's how I do it dynamically. This is my template where if I see traffic with the color 100, I'm going to put it into a policy with flex algo 128. Again, that's the template. In SR-PCE, we now have a router, and this is maybe the first time that you will see if you haven't experienced SR-PCE. I have a router that now has 2 locators prefixes. These describe their identity in the microseed world. I have a blue locator that represents COM to 2 following the IGP. So it is a /48 IPv6 prefix. And I also have a min delay locator in red that means follow the flex algo 128 to me. These 2 locator prefixes will be advertised in ISIS. So the routers will actually have routing programmed for those /48 prefixes. And that's not the point, the full point of what I want to show you. What I want to show you now is how do I do the steering into the algo directly. When you configure a service in SR-PCE, like here, VPN 9, you tell the egress router from which locator you want to assign service functions. So in this case, I'm saying service VPN 9 belongs in locator best effort slice. Therefore, in BGP, if you look at the top, it says with SID, and then with the violet dotted line, he's advertising his blue locator with a hex number at the end, FOX009, that's my decapsulation function. This is what used to be my VPN label. So now you can see that the BGP route for the service route includes the transport FCVV VV00. That's my blue locator. It's telling me which transport do you want to come to me, and then it includes the service decapsulation function F009. Therefore, when router 1 gets that route in VPN with that service seed, he will do IP in IP, and the destination outer IPv6 address is the SR-PCE seed address value. And you go over the flex algo directly. No policy, no other complexity. I could have another service. In this case, it's still VPN 9, but now I'm going to tell VPN 9, you are part of the locator min delay. So that service will be allocated a function from the min delay locator. Therefore, I'm going to realize transport to that node 2 for that VPN over the min delay slice. So as you can see again, BGP route is advertising all the constructs that include transport construct and service construct. Very important. We have 5 minutes, right? 5 minutes? Very good. So what are some of the operational considerations for FlexAlgo? As I said, you are now exposed to your own FlexAlgo attributes, T metrics, affinities. Use them. Minimize, because routers could take a legacy TE and advertise it as FlexAlgo, but don't do it. You're adding more complexity to the implementation, and at the end, you just want to have a clean slate. Configure your FlexAlgo TE metrics separately from, even though they are the same value. don't make the router guess. It's not a guess, there are rules, but don't make us use that code. Put your metric. And that applies especially when you do the TE metric. How many flex algos can I have? So very importantly is don't treat the flex algo as a one-to-one service exclusivity object. I'm not doing flex algo for customer 1, flex algo X for customer B. No. A flex algo represents a type of transport intent, and think of it like mean delay. Everybody who wants mean delay, write on that flex algo. Okay? So the flex algos are shared. Therefore, and what I mentioned earlier, we can see single-digit numbers, 5, 6, 7, 8, 9. And we recommend staying within the single digit. When you ask a router to belong to multiple flex algos, we say keep it below 10 flex algos. And when you configure your sRGV size or you plan for it, you take the flex algos into consideration because you will need more labels considering flex algo, and I already gave you that piece of advice at the beginning. With the time we have left, what we're going to do is we're going to cover this last section. And then when you look at the deck offline, you will see extra collateral. Feel free to review and ask me questions through the WebEx space. Or if not, in the WebEx space, I will put my email, and then you guys can email me. But what I want to cover last is what we call SR performance monitoring. SR was born 13 years ago for SR-MPLS. We have been shipping it since 2015, 14. 15 is the first deployment, and the plumbing is done. And what I think is the next frontier, and we are delivering on it, is how do you monitor this transport? Do I have all the tools to be able to feel that I have enough coverage to monitor the tools? And this is what we do with SR-PM. We do monitoring. And in this slide, we summarize a lot of the different techniques we have for monitoring. But don't look at it now. Pay attention to what I'm going to say first. We try to simplify the monitoring. And we do that by applying source routing principles. Meaning, if I want to detect liveness, I want to check that my path is really working from me to him. In the old days, I will have a BFD session, and now BFD needs to run. I need to bootstrap it, BFD come up. No. Hold on to that. What happens if I do source routing, and I send a packet that has 2 labels, one label to go to him, and it includes the label to come back to me? He's clueless. I'm not setting up a BFD session. I'm doing liveness with source routing because now I know what instruction he will use to come back to somewhere else. So think in those terms. It's really simplifying how you even do per PM by being able to enforce a return path. Okay? But so here you have box number 1. We can do PM probes. This is all TWAMP-based, TWAMP Lite, to measure the delay on a link. So that's step number 1 there. I like box 5. I have an SR policy. From these 2 violet boxes, I want to measure the delay over the SR policy. That's my SRTE policy probe. I like to have a probe on a router where I'm hitting a device outside of the MPLS domain. I'm hitting a CE, so I'm doing a probe between PE and CE, local CE, or a probe PE to remote CE. And all I need to know is that these CEs are, or those stations are TWAMP capable. I'm going to have a TWAMP packet going towards those IP. And if I need to go from the left to the right across a VPN, the probe will impose the VPN label. So the transport will be taken care. Cisco also made recently an acquisition of a company called Axidian. So in box number 4, we welcome them from the probe, external probing world, where I can have Axidian probes that are running on an SFP, a pluggable on the router, or a probe that is sitting on a NID device in the customer prem. Yeah.
So are they special
Yeah, so in particular, what I mentioned, these are Axidian SFPs. Yeah, they're special SFPs. They have the extra capabilities. So, so with that, I'm going to stop here. I'm going to say that there is one section that was not covered, but you have it there in the materials. I think I just wanted to finish with the conclusion. The conclusion is actually quite simple. I hope eventually that you are able to get a grasp of what we're trying to do with SR, which is there are many ways how you can tackle a problem, but always the best way is the simple way. So it is really our challenge with SR is to really find the simplicity in the solutions. And as you can see, things as rich as SRTE, automated steering, also looking for things that are new, that were never possible before. So that's our mantra. And with that, I think we try to stay to it. If you want to be informed about these things in general, we recommend a few resources. The segmentrouting.net website is an external site that has a lot of material in the SR world. And there are some segment routing textbooks, literally textbooks, 800 pages of SR that you can review on your own. Lastly, if you remember my accent, please remember to fill up the survey and give us the feedback. We take the feedback very seriously and try to improve for next year. So if you have a moment, please fill it up. And I want to thank you. I hope you have a good show. And if you have any questions, I'll be here and outside.